Here's a question that feels ridiculously simple, but might actually be the most terrifying thing you can ask a physicist. When is now? I don't mean what time is it. I mean, where is this boundary we call the present moment? You are hearing my voice right now. You are sitting in a chair, or walking, or driving right now. It feels like the only thing that's real. The past is a ghost, the future is a fantasy. The only reality is this razor-thin slice of existence we call the present. But here's the problem. According to our best maps of the universe, that razor-thin slice doesn't exist. It can't exist. If you ask Einstein, the now is a stubborn illusion. If you ask a quantum physicist, the now is a blurry cloud of probabilities that hasn't made up its mind yet. And if you try to pin down exactly what physics says about this moment, this exact split second where you and I are connecting, you find yourself standing on a fault line between the two greatest theories in history, watching them scream at each other. So today, we're going to step into that crack. We're going to look for the present moment. We're going to find out why Einstein killed it, why quantum mechanics is trying to resurrect it, and why the reality of your life depends on which one of them wins. Part 1. The loaf of bread. To understand why the present moment is such a headache for physicists, we have to go back to a time when it wasn't. We have to go back to Isaac Newton. For Newton, the universe was like a giant master clock. It ticked at the same rate for everyone, everywhere. If it was now for you in London, it was simultaneously now on Mars and now in the Andromeda galaxy. Time was a container. It was absolute. It flowed like a steady river, carrying the whole universe along with it at the exact same speed. This is how we intuitively feel the world works. We feel like we share a now with everyone else. If I snap my fingers, we imagine that snap happens across the entire universe at the exact same instant. But in 1905, Albert Einstein came along and essentially smashed that clock with a sledgehammer. With special relativity, he proved that time isn't a rigid container. It's flexible. It stretches and squashes depending on how fast you're moving. And this leads to one of the most mind-bending concepts in all of physics, the relativity of simultaneity. It sounds technical, but let me break it down with an analogy that physicists love. It's called the space-time loaf. Imagine the entire history of the universe, past, present, and future, is a giant loaf of bread, a long baguette of existence. One end is the Big Bang, the other end is the heat death of the universe. Now, how do you define now? Well, you take a knife and you slice the bread. That slice is the present moment. Everything in that slice is happening at the same time. Here is Einstein's insight. The angle at which you cut the bread depends on your speed. If you and I are sitting still together, we cut the bread at the same angle. We agree on what now is. We share the same slice. But if you get up and start walking, just walking, you don't even need to be in a rocket ship, your angle changes. Because you are moving relative to me, your definition of simultaneous tilts. You are slicing the bread at a slightly different angle. Now, at human speeds, this tilt is tiny. It's negligible. But let's scale it up. Let's look at the Andromeda paradox. Imagine an alien living in the Andromeda galaxy, which is about 2.5 million light years away. Now, imagine this alien starts walking toward Earth, just a slow, casual walk. Because of that vast distance, even that tiny walking speed tilts their now slice drastically relative to ours. If they are standing still, their now might line up with our now, but the moment they start walking toward us, their slice of the present tilts into our future. Suddenly, their now contains an Earth that hasn't happened for us yet. They are technically sharing a present moment with an Earth that hasn't happened for us yet. And if they turn around and walk away from Earth, their slice tilts into our past. Their now includes an Earth from last week. Do you see the implication here? If simply walking across a room can change what exists in the present for a distant observer, then there is no such thing as a universal distinctive now. You can't draw a sharp line across the universe and say, everything here is happening at this instant. This leads to a view of the universe called eternalism, or the block universe. In this view, the loaf of bread is already baked. The past, the present, and the future all exist simultaneously in a four-dimensional block. The dinosaurs are still alive back there in the past. Your great-grandchildren are already alive up there in the future. We just happen to be conscious of this specific slice, like a spotlight moving across a dark stage. But the stage is all there, all the time. Einstein found a strange comfort in this. When his best friend Michele Besso died, Einstein wrote a letter to Besso's family. He said, "Now he has departed from this strange world a little ahead of me. That means nothing. People like us who believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion." For Einstein, the present wasn't a feature of reality. It was a trick of the mind.
Part 2. The Quantum Rebel.
So relativity tells us the present is a lie. The block universe says everything is frozen in amber. Case closed, right? Well, not quite, because while Einstein was busy dismantling time, another group of physicists was building a theory that seems to desperately want it back. Enter quantum mechanics. If relativity is the study of the massive and the fast, quantum mechanics is the study of the tiny and the weird. And down at the level of atoms and electrons, the story of time gets completely different. In the standard view of quantum mechanics, the Copenhagen interpretation, particles don't have definite properties until you measure them. An electron isn't here or there. It's in a superposition, a fuzzy cloud of probability. It is essentially in all possible places at once. But the moment you measure it, snap, it collapses. It picks a spot. The wave function collapses into a single reality. Here's where it gets messy for time. This collapse appears to happen instantaneously. And I mean instantaneously. Let's look at quantum entanglement. This is the phenomenon Einstein famously called spooky action at a distance. You can take two particles, entangle them so they share a single quantum state, and then separate them. You put one in a lab in Paris and the other on the moon. According to quantum mechanics, if you measure the particle in Paris, the particle on the moon instantly knows what happened and adjusts its state to match. Instantly. Faster than the speed of light. Do you see the problem? Einstein's whole theory of relativity is built on the idea that nothing travels faster than light, and that instantly is a meaningless word, because everyone's now is different. But quantum mechanics seems to imply that there is a background heartbeat to the universe. If the particle on the moon reacts at the exact same moment the particle in Paris is measured, that implies there is a universal moment connecting them. It implies there is a true absolute now that sits underneath the fabric of space-time, ignoring the rules of relativity. This is the great conflict, the problem of time. In general relativity, time is a bendy, stretchy dimension just like space. It's a coordinate. It's part of the landscape. In quantum mechanics, time is usually treated as a background parameter, a steady metronome ticking away outside the system, driving the evolution of the wave function. The Schrödinger equation, which is the holy grail of quantum math, has a little t in it for time, and that t looks suspiciously like the old-fashioned absolute time that Newton loved. So we have two maps of reality. One says the now is a subjective illusion caused by your perspective. The other suggests the now might be a fundamental instantaneous collapse of reality happening everywhere at once. They can't both be right, and the fight between them has led some physicists to propose something even more radical. What if time itself isn't real at all? Part 3. The Land of Timelessness. If you really want to have an existential crisis, you have to read the work of Julian Barbour. He's a British physicist who has spent decades arguing for a concept he calls the end of time. Barbour looks at the conflict between relativity and quantum mechanics and says, you know why we can't unify these two theories? Because we're trying to keep time in the equation. We need to kill it completely. His theory is called Platonia. Imagine a vast landscape, but instead of hills and valleys, every point on this landscape is a configuration of the universe. One point is the universe where the dinosaurs are just hatching. Another point is the universe where you are listening to this sentence. Another point is the universe where you just spilled your coffee. Barbour argues that all these snapshots exist eternally. They are all real, but there is no river of time connecting them. There is no flow. He calls these snapshots nows, but they aren't arranged in a sequence. They're just scattered, like a deck of cards thrown on the floor. So why do you feel like you're moving through time? Why do you have memories of the past? Barbour says it's because of the structure of the snapshot itself. The snapshot of you listening to me contains within it the neural patterns, the memories of the snapshot where you pressed play 5 minutes ago.
Your brain is wired to hold data that looks like a history, but that history is just part of the static picture of this moment. It's like looking at a fossil. When you see a fossil in a rock, you tell yourself a story about a dinosaur that lived millions of years ago. But the fossil is just a rock, sitting there now. The evidence of the past is actually just a structure in the present. In Barber's view, the present moment is the only thing that exists, but it's not a moment in time. It's a location in configuration space. We aren't moving through time. We are just inhabiting a specific slice of the possible. It is a beautiful, icy, crystalline view of the universe. It solves the conflict between relativity and quantum mechanics by erasing the battlefield. If nothing moves, nothing has to travel faster than light. If nothing flows, you don't need to synchronize clocks. But for many of us, this is unsatisfying. It feels wrong. We feel the flow. We feel the becoming. Is that feeling just a chemical trick? Or is physics missing something fundamental about how reality unfolds?
Part 4, the thermodynamic error. This brings us to a more modern and perhaps slightly more human perspective. The physicist Carlo Rovelli has become a bit of a rock star in the physics world for his book, The Order of Time. Rovelli agrees with Einstein that at the fundamental level, time disappears. If you zoom in to the smallest scales, the Planck scale, there is no t variable. The equations of loop quantum gravity, which is Rovelli's field, don't have time in them. They just have relations, variables changing relative to other variables. But, Rovelli says, just because time isn't fundamental doesn't mean it's not real for us. He uses the analogy of temperature. If you look at a single molecule of water, it doesn't have a temperature. It just has speed. Hot and cold are statistical averages. They only emerge when you have billions of molecules bumping into each other. Temperature is an emergent property. Rovelli argues that time and the present moment are exactly the same. They are emergent properties born from our specific perspective on the universe, specifically from entropy. Entropy is the measure of disorder. The second law of thermodynamics says that entropy always increases. Things break, coffee cools down, eggs scramble. This is the only law in physics that has a direction. It points from the past, order, to the future, disorder. Rovelli suggests that our sense of the present is basically us surfing the wave of entropy. We are macroscopic creatures. We don't see the microscopic timelessness of the atoms. We see the big, blurry averages. And in that blurry vision, we see a flow. We see a now that eats the future and leaves a trail of past behind it. But here is the kicker. This flow is local. It's not universal. Rovelli brings us back to the idea that the present is a bubble. My present is real for me. Your present is real for you. If we are close to each other, our bubbles overlap enough that we can pretend they're the same. We can agree on a shared reality. But we cannot extend that bubble to the stars. The now is like a campfire. It provides light and warmth for those huddled around it, but its light fades the further out you go. There is no bonfire that warms the whole universe at once. So, what does physics say about the reality of the present moment? It says that the present is a relationship. It is not a stage where the universe performs. It is a local phenomenon created by the interaction of matter, the limit of light speed, and the statistical blurring of our own brains. Einstein was right. There is no universal sheet of now slicing through the cosmos. But the quantum physicists are right too. The collapse, the interaction, the measurement, that is where reality happens. But it happens locally. Your now is valid. It is the only place you can ever exist. It just isn't the only now. We live in a universe of billions of little private time bubbles floating in a timeless block, occasionally bumping into each other and sharing a moment. And honestly, I think there's something kind of poetic about that. It makes the moments where our nows do overlap, like this conversation, feel a little bit more miraculous. If you enjoyed this deep dive into the cracks of reality, share this episode with a friend whose now slice you appreciate. It helps the show more than you know.